Okay, hi everyone. Now we discuss atomic structure, quick revision, some important points from atomic structure. Okay, we know atomic structure deals with arrangement of various particles in an atom. What is the constitution of atom? Okay, what are the various particles present in an atom and how they are arranged? Okay, that we'll discuss. So first, if you see Dalton's atomic theory, according to Dalton's atomic theory, we know if you cut matter into various pieces, the ultimate piece obtained, the final piece obtained is said to be atom, which is not further indivisible or uncuttable. So atom is the ultimate particle obtained if you cut matter into various pieces according to Dalton's atomic theory. Okay. But later various scientists discovered many particles inside the atom. Out of those, fundamental particles are what? Electron, proton and neutron. So out of these three, these two present under nucleus, so they are said to be nucleons. Okay, some of the properties of these, if you see, what about mass of electron that is required? That is 9.1 into 10 power minus 28 grams or 10 power minus 21 kgs. That is the mass of electron. What is the charge on the electron? Negative, and quantity is, magnitude is 1.602 into 10 power minus 19 coulombs. 1.602 into 10 power minus 19 coulombs. Proton mass is 1837 times, almost more to electron. Neutron mass almost 1840 times. This is 1837 times. This is 1840 times more compared to electron. The charge on the proton is positive, magnitude is same, 1.602 into 10 power minus 19 coulombs. Neutron is neutral, no charge. Okay, and the spin of all these three is 1 by 2. As spin is 1 by 2 of integral spin, those are said to be fermions. Electron, proton, neutron are called fermions. Okay, so next one. Okay, in the electromagnetic radiation, energy, what is the energy expression? E is equal to h nu. Nu may be written as C by lambda. 1 by lambda may be written as nu bar. Nu is called frequency, that is the number of waves crossing a particular point within a given time. As frequency increases, energy also increases. Wavelength, okay, that is nothing but one complete cycle length, and this is half wave, this is half wave, one complete cycle length, or the distance between two successive crests or two successive troughs. The distance between two successive crests or troughs is called as wavelength. Wave number, within 1 centimeter distance, how many waves are present, that is called as wave number. For example, distance is 1 centimeter. Within 1 centimeter distance, how many waves are present, that is called wave number. As wave number increases, energy increases. As wavelength increases, energy decreases. C is called velocity of light. Velocity of light, that is 3 into 10 power 8 meter per second or 3 into 10 power 10 centimeter per second. Okay, and h is called Planck's constant, whose value is 6.62 into 10 power minus 27 erg second or 6.62 into 10 power minus 34 joule second. Okay, so this is the expression for energy of one photon, and E is equal to h nu or hc by lambda or hc nu bar. Nu bar wave number, lambda wavelength, and nu is the frequency. Okay, so various regions present under electromagnetic radiation are, if you write in the increasing order of energy, radio waves, next to microwaves, next to IR radiation, visible, UV, next to X-rays, gamma rays and cosmic rays. This is in the increasing order of energy. Therefore, what about wavelength? Decreases, energy increases, so wavelength decreases, frequency increases, wave number also increases from left to right. Okay, this is the order of increasing of energy. And we know UV visible radiation range, if you see, 200 to 800 nanometers UV visible radiation. In that UV almost 200 to 400 nanometers. Visible 400 to 800. In some of the books it is given 760, 700 like that. So 400 to 700 or 700 to 800 range and visible radiation. Okay, wavelength range. Right. So next one, Planck's quantum theory. So according to Planck's quantum theory, okay, we know according to classical mechanics, energy emission or absorption takes place continuously. But according to Planck's quantum theory, energy absorption or emission takes place discontinuously in the form of packets. Each packet of energy is called quantum. Each packet energy is called quantum, and energy associated with quantum or each packet is proportional to its frequency. So if you remove the proportionality, you will get Planck's constant. Okay, some of the assumptions in Planck's quantum theory are energy emission is discontinuous in the form of packets. Each packet energy is called quantum. Energy associated with each quantum is proportional to its frequency. And third one is energy is quantized. Quantization of energy is explained by Planck's. Energy is quantized means whether energy levels are continuous or finite energy levels present. Finite energy levels, some discrete energy levels are present. If finite energy levels are possible, then energy is said to be quantized. Okay, these are some assumptions in the Planck's quantum theory. So next one, de Broglie's wave particle duality. De Broglie's wave particle duality. So we know light possesses both particle nature and wave nature. Some of the properties of light we can explain based on particle nature, and some of the properties we can explain based on wave nature. For example, diffraction, refraction, interference, those we can explain based on wave nature. Photoelectric effect, Compton effect, we can explain based on particle nature. Photoelectric effect and Compton effect we can explain based on particle nature. So light possesses both particle and wave nature. The similar concept extended by de Broglie to matter, okay, particularly to microscopic particles like electron, atom, proton, molecules. Okay, whenever they are under motion, microscopic particles, whenever they are under motion, they possess both wave nature and particle nature. That means dual nature. They possess dual nature. Okay. Right, that is called de Broglie's wave particle duality. Okay, so the expression for wavelength, if you see, the expression for wavelength is h by mv, or with respect to momentum, linear momentum, m into v is called p, or with respect to kinetic energy we can write as p is equal to square root of 2em. With respect to kinetic energy we can write as square root of 2em, where e is kinetic energy. Or with respect to charge on the particle and applied potential, kinetic energy given as 2 into q into Vm. Kinetic energy can be written as q into V. If q is the charge on the particle and it is accelerated by a potential of V, then kinetic energy is given as qV. And another expression with respect to temperature, that is h by 2 pi m kT whole power 1 by 2. H by 2 pi m kT whole power 1 by 2. So from this, these are the various expressions for wavelength we have. From this, lambda is inversely proportional to momentum. Lambda is inversely proportional to temperature. So as temperature increases, what about wavelength? Decreases. As temperature increases, wavelength decreases. These are the various expressions for wavelength. For example, if you apply specially to electron, what is the expression for wavelength of electron? We know charge on the electron 1.60 into 10 power minus 19 coulombs. Mass of the electron is known to us. Planck's constant is known to us. If you substitute all those constants, we will get square root of 150 by V in volts. That we will get in angstroms. And this is the expression for wavelength of electron, square root of 150 by V in volts, angstroms. This is about de Broglie wave particle duality. Next one, Heisenberg uncertainty principle. According to Heisenberg uncertainty principle, both position and momentum we cannot determine simultaneously and precisely. So one we can determine with more precise, another one we cannot determine with more precise, or we can determine with less precise. For example, position we can determine exactly, momentum we cannot determine exactly. One we determine with more precise, another one we cannot determine with more precise. So the properties which we cannot determine simultaneously and exactly, those properties are called conjugate properties. So position and momentum are called as conjugate properties. Let us consider uncertainty in the position delta x, uncertainty in the momentum delta p. Then according to Heisenberg uncertainty principle, we have delta x into delta p greater than or equal to h by 4 pi, or we can get h bar by 2, where h bar is called reduced Planck's constant, h by 2 pi. H bar is nothing but reduced Planck's constant, that is h by 2 pi. Okay, and momentum we can write as m into v. So from the delta p we can write as m into delta v, where delta v is uncertainty in the velocity. We can also write like this. And energy and time also conjugate properties. And so similar to position and momentum, we will get delta E into delta T greater than or equal to h by 4 pi. We know E is equal to h nu, so therefore h into delta nu into delta T greater than or equal to h by 4 pi. Okay, energy and time are also said to be conjugate properties. Okay, this is Heisenberg uncertainty principle. Position and momentum we cannot determine exactly and precisely. And here if delta x, if you bring delta p right side, and delta x greater than or equal to h by 4 pi into 1 by delta p. For example, if delta p tends to infinity, what about delta x tends to 0? If uncertainty in the momentum is very, very high, uncertainty in the position is very, very low. Okay, similarly, if uncertainty in the position is very, very high, uncertainty in the momentum is very, very low. Okay, next one, Schrodinger wave equation. Here we are giving Schrodinger time independent wave equation. Schrodinger time independent wave equation, that is dou square psi by dou x square plus dou square psi by dou y square plus dou square psi by dou z square plus 8 pi square m by h square into e minus v into psi is equal to 0. Here psi is called wave function or amplitude of wave function. Here psi we are studying as a function of what? Cartesian coordinates or space coordinates x, y, z. Cartesian coordinates or space coordinates, that is x, y, z. Okay, here psi is independent of time. That's why it is called Schrodinger time independent wave equation. As psi is independent of time, it deals with stationary energy levels. It deals with stationary energy levels. At a particular time, what about various energy levels possible? Stationary energy levels. That's why Schrodinger wave equation follows conservation of energy. Okay, here E is the total energy and V is the potential energy. E is total energy and V is potential energy. This is the Schrodinger time independent wave equation. If you solve this equation, what we will get? Psi, and we will get expression for psi. That psi gives all the information about the system. All the information means we can determine position, momentum, average position, average momentum, kinetic potential energy. All those we can determine by using, kinetic energy. All those we can determine by using psi. And okay, so psi gives all the information about the system. Okay. Now, okay. Now, according to Heisenberg uncertainty principle, exact position of electron we cannot determine. Exact position we cannot determine. So we try to determine what? Probability. We try to determine probability. That probability can be obtained by solving Schrodinger wave equation. If you solve Schrodinger wave equation, we will get psi. Psi may possess both positive values, negative values, and 0 also. But probability cannot be negative. Probability cannot be negative. So psi cannot give information about probability. But psi square possesses always what? Positive values. Psi square gives information about probability or electron density. That is called as Born rule. So what is Born rule? Psi square, or we can write as psi star or mod psi square, that is proportional to probability or electron density. So electron density or probability is given by what? Psi square. And okay, the general expression is psi square d tau, where d tau is volume element. For example, we are studying a particle moving along x dimension in between x and x plus dx. Probability is given as psi square dx. Okay, in between x and x plus dx, what is the probability? Psi square dx. And in 2 dimension we get psi square dx dy. In 3 dimension, psi square dx dy dz. Okay, so for example, I am giving a wave function like this. Here psi value plus 1, for example, here psi value plus 2, for example, here psi value minus 3. Okay, this is first point, second point and third point. 3 points I am giving. First point, second point and third point, where the probability for finding the electron is high. Okay, here psi value plus 1, here psi value plus 2, here psi value is minus 3. Psi cannot give information about probability. Psi square gives information about probability. So at first point, psi square value 1 unit, second point 4 units, third point 9 units. So where the probability is more? At the third point. And so order of probability, if you see, probability at third point is more compared to second point compared to first point, since probability is given by psi square, not psi. And this is called a nodal point. The wave function becomes 0 at this point, that is called a nodal point, psi. And okay, or the nodal point is the one where the wave function changes its sign. Here the wave function changes from positive values to negative values, that is called nodal point. So this is Schrodinger wave equation. Next one, hydrogen atomic spectrum. So atoms possess only electronic transitions. So therefore, in the case of atoms, which type of spectral signals we will get? We will get line spectrum. We will get line spectrum. In the case of molecules, rotational transitions, vibrational transitions and electronic transitions are possible. So we will get bands. Band spectrum is observed in the case of molecules. In the case of atoms, only electronic transitions are possible, so we will get line spectrum. Okay, we will get series of lines. We will get some series of lines. These series of lines are classified into 6 series. And 6 series, those are, okay, series N1, N2, region. The 6 series are, one is Lyman series, Balmer series, Paschen, bracket, fund and Humphrey. These are the 6 series we have. The transition occurs from higher energy levels to first level, and higher energy levels to higher electronic energy level to lower electronic energy level, that is second, third, fourth level to first level, that corresponds to Lyman series. Next 3, 4, 5 levels to second level, Balmer, 4, 5, 6 to third level, Paschen, 5, 6, 7 to and so on, okay, to fourth level, bracket, 6, 7, 8 and so on to fifth level, fund series, 7, 8, 9 and so on levels to sixth level, that is called Humphrey series. And so whenever the transitions occur in the Lyman series, and 2, 3, 4 and so on to first level, the signals are observed in UV region, here visible region, here near IR, next to mid IR, far IR and far IR. These are the regions where we observe spectral lines. And in each series, the first line corresponds to H alpha line. 2 to 1 H alpha line, 3 to 1 corresponds to H beta line, 4 to 1 corresponds to H gamma line. For example, here 3 to 2 corresponds to H alpha line. Here 5 to 3 corresponds to H beta line. Here 7 to 4 corresponds to H gamma line. Okay, first line is indicated as H alpha, second one H beta, third one H gamma, fourth one H delta, and last line infinite level to, okay, sixth level, for example, infinite level to N1 level and infinite level to N1 level, that is called as last line or limiting line, last line or limiting line, or H infinity line and H infinity line. In this case we will get Energy gap is high, infinite level to 6 level means energy gap is high. So in this case we will get shortest wavelength and as gap is high, shortest wavelength we will get. Okay, in each case H alpha line or first line, H alpha line or first line corresponds to what? Longest wavelength in each series. Why it is longest wavelength? Why it is corresponds to longest wavelength? Energy gap is small. 2 to 1 energy gap small, 3 to 2 gap small, 4 to 3 gap small compared to 5 to 3, 6 to 3. 4 to 3 gap is small, 5 to 4 gap is small compared to 6 to 4, 7 to 4. So 5 to 4 is said to be what? H alpha line or first line or longest wavelength. In that case we will get longest wavelength. Next one, if the transition is occurring from N2 level to N1 level, what about the number of lines obtained? The formula for number of lines obtained is summation N2 minus N1. The expression for number of lines obtained is N2 minus N1. For example, 5th level to 3rd level the transition is occurring. 5th level to 3rd level. So the formula for number of lines is summation 5 minus 3, that is 2. So we have to expand like this, and 2 plus 1, 3. For example, 6 to 3, summation 3 we will get, 3 plus 2 plus 1, 6 lines we will get, 6th level to 3rd level. The number of lines observed are, okay, 6 to 3 if you take, we will get summation N2 minus N1, 6 minus 3, that is 3. That means 3 plus 2 plus 1, 6 spectral lines are observed. And in this case 5 to 3, that is one is 5 to 4, next one 5 to 3, next one 4 to 3. And these are the various spectral lines observed. For example, if you take 5 to 2, for example, if you take 5th level to 2nd level, what is the number of spectral lines observed? Summation 5 minus 2, that is 3, that means 6 we are getting. What are those 6? 5 to 4, 5 to 3, 3 to 2, next to 4 to 3, 4 to 2, okay, 5 to 4, 5 to 3, next to 5 to 2 and 5 to 2. Okay, these are the 6 spectral lines possible. Sometimes they may ask you question, how many of them are visible? How many of them are visible? Visible means what? Balmer series. Okay, higher energy levels to 2nd level and how many of these transitions corresponds to 2nd level and are Balmer series and 3 to 2, 4 to 2, 5 to 2, these corresponds to Balmer series. Therefore, how many lines comes under visible region? And 3 lines comes under visible region, 4 to 2, 5 to 2 and 3 to 2. And lastly, selection rules. What are the selection rules? If you see the first selection rule, delta n any integer, so therefore no need to concentrate on this delta n. 7 to 6 possible, 8 to 6 possible, 9 to 6 possible, infinite level to 6 also possible. So delta n is any integer. And so second one is important, delta L is equal to plus or minus 1. And only these, the transitions which follow this selection rule are allowed. And for example, if you take Lyman series means higher energy levels to first level. For example, 3s to 1s, whether it is allowed or not allowed. And not allowed. Since delta L is 0, 0 minus 0, that is 0. Delta L is 0, not allowed. 2s to 1s, not allowed. Okay, higher energy levels to first level, that corresponds to Lyman series. If you take, for example, 3s to 2p, is it corresponds to Lyman series or not corresponds to Lyman series? And not corresponds to Lyman series, but it follows selection rule or not? Yes, it follows selection rules. It is not observed under Lyman series and it is observed under Balmer series. Okay, delta L is equal to 1 minus 0, 1 and plus 1, so that is allowed. And for example, if you take 2p to 1s, right, 2p to 1s, delta L is equal to plus or minus 1, so that is allowed under Lyman series. 2p to 1s is allowed under Lyman series, and like this we have to verify. 3s to 2p is not allowed under Lyman series, but it is allowed under Balmer series. 3s to 2p, higher energy level to 2nd level, that corresponds to Balmer series. This is okay. Next one, to calculate wavelength or wave number of each line, Okay, Rydberg proposed an equation. This is the equation. RZ square into 1 by n1 square minus 1 by n2 square. By using this, we can calculate wavelength or wave number of each line in each series. R is called Rydberg constant. Its value is 1,09,677.8 centimeter inverse. Z is called as atomic number. For hydrogen atom, it is 1. So it is applicable to all 1 electron systems. And helium plus ion 1 electron system, Z value 2. Beryllium 3 plus ion 1 electron system, Z value 4. Lithium 2 plus ion 1 electron system, Z value 3. Okay. So by using this equation, we can calculate wavelength or wave number of each line, okay, in each series. And that is about hydrogen atomic spectrum. Next one, Bohr's atomic model. According to Bohr's atomic model, electron moves around the nucleus in which paths? And circular paths. Electron moves around the nucleus in circular paths. As long as electron remains in that state in a particular orbit, its energy remains constant. That's why these are said to be what? Stationary energy levels or stationary orbits. Okay, they are indicated by 1, 2, 3 and so on. Or K, L, M, N and so on. K corresponds to first orbit, M corresponds to third orbit, N corresponds to fourth orbit. Okay. Next, circumference of orbit. Circumference is given by what? 2 pi r. Circumference of circle is given by 2 pi r is equal to an integral multiple of wavelength. An integral multiple of wavelength where the possible values of n are 1, 2, 3 and so on. If you take first orbit, circumference is equal to 1 lambda. So in the first cycle, how many waves are present? And only one wave is present. Within that one cycle, one wave is present. In the second orbit, 2 pi r is equal to what? 2 lambda. That means within that cycle, how many waves are present? 2 waves are present. Okay. 2 waves length is equal to this length. One wavelength is equal to this length, circumference length. Okay. Circumference of an orbit is equal to n lambda. So from that, 2 pi r is equal to n lambda. Lambda may be written as h by mv. From that we will get mvr is equal to nh by 2 pi. Mvr is called as angular momentum. So the possible values for angular momentum are 1h by 2 pi, 2h by 2 pi, 3h by 2 pi and so on. Okay, 1, 2, 3, those only possible. 1.5, 1.7, those are not possible. That means only some definite values are possible. So angular momentum is said to be quantized. Angular momentum is said to be quantized. So based on these assumptions, Bohr calculated radius, velocity, energy and ionization energy. So these 4 formulas you may remember. What is the expression for radius? 0.529 into n square by z angstroms. The expression for radius is 0.529 n square by z angstroms. So radius is proportional to n square by z. As n increases, radius increases. As z increases, radius decreases. If you fix z as n increases, radius increases. If you fix n as z increases, radius decreases. Okay. If you calculate radius of first orbit of hydrogen atom, radius of first orbit of hydrogen atom, we will get what? 0.529 angstroms. That is indicated as A naught, which is called as Bohr's radius. 0.529 angstroms is called as Bohr's radius. Okay, from this we can write R1 by R2 is equal to N1 square by N2 square into Z2 by Z1. So while we are comparing radius of two 1 electron systems of different orbits, radius of two 1 electron systems of different orbits, that is N1 and N2, in such cases this equation is helpful. Okay, this is about radius. Next, velocity of electron. The formula is 21.84 into 10 power 7 Z by N centimeter per second. So velocity is directly proportional to Z by N. As Z increases, velocity increases. As N increases, velocity decreases. So V1 by V2 is equal to what we get? Z1 by Z2 into N2 by N1. V1 by V2 is equal to Z1 by Z2 into N2 by N1. Next one, energy. This is important. Total energy is equal to potential energy plus kinetic energy. So potential energy expression is minus 27.2 Z square by N square. And potential energy expression is kinetic energy plus 13.6 Z square by N square, that is in electron volts. This is the expression for potential energy. This is the expression for kinetic energy. So we will get energy expression minus 13.6 Z square by N square. This is the total energy expression. So therefore, if you see the ratio of total energy, potential energy and kinetic energy, okay, this is minus 13.6 Z square by N square, minus 27.2, minus 13 plus 13.6. And the remaining parameters constant. Here we have minus 13.6 minus 27.2 is to plus 13.6. So we'll get, if you divide with the 13.6, we are getting minus 1 is to minus 2 is to 1. This is the ratio of total energy to potential energy and kinetic energy for one electron systems. Okay, this is in electron volts. And this is in electron volts. So if you see the various expressions for energy of electron present in nth orbit for one electron systems, minus 13.6 into Z square by N square, that is in electron volts, minus 2.18 into 10 power minus 18 Z square by N square, that is in joules. Next, minus RHC Z square by N square. This is with respect to Rydberg constant. Next, another one is minus Z square by 2 N square, that is in atomic units. Minus Z square by 2 N square in atomic units. These are the various expressions we have for energy. Main important one is this one, minus 13.6 into Z square by N square electron volts. So one thing, if you observe, energy here depends only on principal quantum number. Energy is independent of azimuthal quantum number. Energy depends only on principal quantum number. So therefore, in the case of one electron systems, 1s, okay, first shell only 1s orbital is possible. In second shell we have 2s subshell and 2p subshell. In 2s we have 1 orbital. In 2p we have 3 orbitals. In 3p third shell, and in third shell we have 3s, 3p, 3d subshells. Okay, in 3s 1 orbital, in 3p 3 orbitals. In 3d we have how many orbitals? 5 orbitals. Okay, energy depends only on n, and that's why 2s 2p possess same energy. 3s 3p 3d possess same energy. Energy is independent of L. Okay, so therefore, what about orbital degeneracy? And what about orbital degeneracy in the case of one electron systems? Okay, here only 1 orbital is there, so 1. Here 4 orbitals we have 4. Here 9 orbitals we have. So the expression for orbital degeneracy is n square. The expression for orbital degeneracy is n square. Shell number square, and 1 square 1. Here 2 square 4. Here 3 square 9. Fourth shell 4 square. 16 orbitals possess the same energy. 16 orbitals possess same energy in fourth shell. For example, I am giving energy expression like this, minus 13.6 by 16 electron volts. What about degeneracy? And in the place of n square, what we have? 16 for hydrogen atom. So 16 is the degeneracy, and 16 is the degeneracy. Okay. For example, for helium plus ion, I am giving minus 54.4 by 9 electron volts. Okay. Minus 13.6 into Z value for helium 2 square 4, minus 13.6 into 4, minus 54.4. So in the place of n square, what we have? 9. So degeneracy is 9. So degeneracy is 9. This is about energy. Next one, ionization energy. Ionization energy. Initially electron is present in nth level. When we say that electron is removed, the energy required to remove the electron is called what? Ionization energy. So if you excite the electron to infinite level, if you excite the electron to infinite level, we can say that an electron is removed completely from the system. So ionization energy is nothing but the gap between E infinity and En. So E infinity, what is the expression for En? Minus 13.6 into Z square by N square electron volts. But if you substitute n is equal to infinity, we will get 0. So this is 0. Minus En means ionization energy is equal to plus 13.6 into Z square by N square electron volts. This is the general expression for ionization energy. If n is ground state, first state and n value 1, hydrogen atom, Z is 1. So ionization energy of hydrogen atom in ground state is what? 13.6 electron volts. And so ionization energy of other atoms is ionization energy of hydrogen atom into Z square. Ionization energy of one electron systems is equal to what? Ionization energy of hydrogen atom into Z square electron volts. Since 13.6 is the ionization energy of hydrogen atom in ground state, Z value 1, N value 1, if you substitute 13.6 we are getting. Okay. So ionization energy of other one electron systems is equal to ionization energy of hydrogen atom into Z square. For example, ionization energy of hydrogen atom is X. What is the ionization energy of lithium 2 plus ion? X into 3 square, 9x. Okay. This is about ionization energy. So this is about Bohr's atomic model. Some limitations in the Bohr's atomic model are it failed to explain many electron systems. It is applicable to only one electron systems. Next, Zeeman effect and Stark effect is not explained. Further splitting of lines in the presence of electric field and magnetic field is not explained. Electric field is called Stark effect. Magnetic field is called what? Zeeman effect. Further splitting of lines. Okay. So fine spectrum is not explained by Bohr's atomic model. Okay. We have Sommerfield's atomic model. Briefly I will explain. According to Sommerfield's atomic model, both circular orbits possible and elliptical orbitals also possible. Both circular and elliptical orbits possible. If you take shell number n and if you take shell number n, in shell number n, one is a circular orbit and all the remaining are elliptical orbits. Only one circular orbit is possible. All the remaining are elliptical orbitals. For example, shell number 3, if you take one circular orbit and two elliptical orbitals are present. Okay. Bohr considered only principal quantum number. Sommerfeld considered principal quantum number and azimuthal quantum number also. Okay. Next one. Photoelectric effect. Photoelectric effect. Okay, on metal surface, if you apply light energy, if electrons are ejected, that is called photoelectric effect, and these electrons are called photoelectrons. On metal surface, we are applying light energy, then electrons are ejected, that is called photoelectric effect. Electrons are called photoelectrons. This is observed in alkali or alkaline earth metals. Since alkali or alkaline earth metals ionization energy values are low, easy to remove the electrons. That's why alkali or alkaline earth metals generally used in photoelectric cells to convert light energy to electric energy. And as electrons are emitted, they are used in photoelectric cells. Particularly cesium ionization energy value is very low. That is used in photoelectric cells. Okay, this experiment indicates which nature of light? Particle nature of light. Okay, so we are applying light energy and h nu. In that, the energy required to remove the electron is h nu naught. This is called as work function or threshold energy. This is the minimum energy required to remove the electron. This is the incident radiation energy and applied radiation energy. So, if you apply radiation energy which is greater than threshold energy work function, the remaining will be converted to what? Kinetic energy of ejected electrons. So h nu is equal to h nu naught plus kinetic energy, or kinetic energy we can write as half mv square. From that we can get velocity of electrons. Okay. Next. Okay, here nu is the incident radiation frequency, nu naught is the threshold frequency. That is the minimum frequency required to eject the electron. H nu is called incident radiation energy, h nu naught is called threshold energy, that is the minimum energy required to eject the electron. For example, if nu is less than or equal to nu naught, then whether electrons are ejected or not ejected, not ejected. If nu is greater than or equal to nu naught, then only electrons are ejected. Okay, for example, if nu is greater than or equal to nu naught and I am further increasing frequency, and for example, nu naught is 10 units and I am applying 10 units, 12 units, 14 units like this. Okay, 10 units is enough to remove the electron, and the remaining 2 units may be converted to what? Kinetic energy. Here the remaining 4 units may be converted to kinetic energy. That means if nu is greater than or equal to nu naught, and as nu increases, what happens? Kinetic energy of ejected electrons increases, and kinetic energy of ejected electrons increases. Since every time only 10 units is required to eject the electron. Next one, if nu is greater than or equal to nu naught, and if you increase intensity, what happens? If you apply more number of photons, what happens? Number of ejected electrons increases. If you apply 10 photons, 10 electrons are ejected. If you apply 20 photons, 20 electrons are ejected. So as intensity increases, what happens? Number of ejected electrons increases. And this is photoelectric effect. This is phenomena is also used in X-ray photoelectron spectroscopy. By using X-ray photoelectronic spectroscopy, we can calculate binding energies or ionization energies. And finally, some points regarding quantum numbers. We know n represents what? Shell number. N represents shell number. As n increases, size increases, radius of orbit increases, energy increases. We discussed velocity decreases as n increases. N represents shell number or orbit number. Next, L, azimuthal quantum number. The possible values for L are 0, 1, 2, 3, so on up to n minus 1. L represents what? Subshell. It represents what? Subshell. Or it also gives orbital angular momentum. That is given by square root of L into L plus 1 h bar. If L is equal to 0, the corresponding subshell is called S subshell, 1 P subshell, 2 D subshell, and 3 F subshell. Okay. Next one, number of subshells in a shell. And number of subshells in a shell. What is the formula for number of subshells in a shell? The formula is what? N. And in first shell, one subshell is present, 1s. In second shell, 2 subshells are present, 2s, 2p. In third shell, 3 subshells are present, 3s, 3p, 3d. So number of subshells in a shell is equal to n. Okay, L is called as azimuthal quantum number or orbital angular momentum quantum number. It represents subshell in a shell. Angular moment we can calculate like this. Number of subshells in a shell is n. Next, M, magnetic quantum number, that represents RML. How many orientations taken by a subshell in the presence of magnetic field? The number of orientations taken by subshell in the presence of magnetic field, or it gives number of orbitals in a subshell. Okay, what is the number of orientations taken by a subshell or number of orbitals in a subshell? The formula is 2L plus 1. Okay, S subshell takes how many orientation? L is equal to 0, 1, only one orientation. P subshell 2 into 1 plus 1, 3 orientation. D subshell 5 orientations. F subshell 7 orientations. Okay, number of orientations that is given by 2L plus 1 or number of orbitals in a subshell that is given by 2L plus 1. The possible values for ML are minus L2 plus L including 0. Minus L2 plus L including 0. Okay. Now, what is the maximum number of electrons? Maximum number of electrons in a subshell. Maximum number of electrons in a subshell. Each orbital carries maximum of 2 electrons. The number of orbitals are 2L plus 1. So each orbital carries maximum of 2 electrons. So therefore maximum number of electrons in a subshell is 2 into 2L plus 1. Okay. Next one, spin quantum number. Spin quantum number. Electron which is moving around the nucleus also moves with respect to its own axis. The electron which is moving around the nucleus also moves with respect to its own axis. So electron possesses intrinsic spin angular momentum that is given by spin quantum number. Spin angular momentum is given by spin quantum number that is equal to square root of S into S plus 1 h by 2 pi. S into S plus 1 h by 2 pi. Okay. S and MS and S and MS similar to L and ML and S and MS similar to what? L and ML. Okay. Here S is called spin quantum number. Spin quantum number for an electron is 1 by 2. spin quantum number for an electron is 1 by 2. Okay, so ms, and that gives orientation of electron. What is the orientation of electron present in orbital? And so n shell, l subshell, ml number of orientations taken by a subshell or number of orbitals in a subshell. This ms gives what? What is the orientation of electron present in an orbital? Upward orientation or downward orientation? For upward orientation it is plus half. For downward orientation it is minus half. Okay. The number of orientations taken is again 2s plus 1, similar to 2l plus 1. 2 into 1 by 2 plus 1. So the number of orientations taken by an electron in the presence of magnetic field is 2. The number of orientations taken by an electron in the presence of magnetic field is 2. This is similar to 2l plus 1. Okay. So finally, what about the number of orbitals in a shell? Number of orbitals in a shell, that is given by n square. In first shell only 1s orbital, 1s orbital. In second shell 2s, 2px, 2py, 2pz, 4 orbitals we have. In third shell 3s, 3p subshell 3 orbital, 3d subshell 5 orbital, 5 plus 3 plus 1, 9. So number of orbitals in a shell is equal to n square. So what is the maximum number of electrons? Maximum number of electrons possible in a shell, that is given by 2n square, since each orbital carry maximum of 2 electrons. So maximum number of electrons in a shell is 2n square. So these are some formula, some points regarding quantum numbers. Okay, we know Pauli's principle. According to Pauli's principle, no 2 electrons in an atom possess the same 4 quantum numbers. For example, if you take 1s2, what about the quantum numbers n, l, m, s values? Both belongs to first shell, both belongs to s subshell. So l is 0, m is also 0. For one electron, if s is plus half, for another electron s is minus half. So no 2 electrons possess the same 4 quantum numbers. That is called Pauli's principle. What about Hund's rule? If we have 2p4, how to fill the electrons? Okay, these are the 2 possibilities we have. So which one is correct? And the second one is correct. Hund's rule of maximum spin multiplicity. If spin multiplicity is high, energy is low, stability is high. And this is the correct one and this is wrong. So while we are filling the electrons in degenerate orbitals, first we have to distribute one electron to all the orbitals, all the degenerate orbitals. After that only we have to pair. Right? We have to distribute one electron to these 3p orbitals. After that only we have to pair. So this is the correct configuration. Okay, so that is Hund's rule. Next one, Abbo's principle. It is also called as building up principle. We have to fill the electrons according to increasing order of energy. According to Abbo's principle, we have to fill the electrons according to increasing order of energy. So energy we can give based on n plus l rule. And energy we can give based on n plus l rule. For example, we have 3s and 2s. And what about n plus l? And 3 plus 0, here 2 plus 0. So n plus l is here 3, here 2. And so it possesses lowest energy. And so order of energy is 2s less than 3s. So first we have to fill 2s, after that 3s. First we have to fill 2s, after that 3s. Okay, for example, I am taking like this, 2p 3s. What about n plus l? 2 plus 1, that is 3. 3 plus 0, that is 3. So both have same n plus l value. If 2 orbitals have same n plus l value, then the orbital which possesses lowest n value, that possesses lowest energy. That is order of energy is 2p is less than 3s. That means first we have to fill 2p orbitals, after that 3s orbital. So according to Abbo principle or building up rule, we have to fill the electrons in the increasing order of energy. Energy we can give based on n plus l rule. Okay, and we know off-filled orbitals or completely filled orbitals are more stable compared to partially filled orbitals. And among off-filled and completely filled orbitals are more stable. That is symmetric distribution of electron density. Another one is exchange of electrons or exchange energy. So those 2 reasons are there for extra stability and in the case of completely filled orbitals, and symmetric distribution of electron density is observed. Another one is exchange of energy or exchange of electrons takes place and okay. This is about atomic structure briefly and one more thing, electron and the charge on the electron is confirmed by what? Millikan oil drop experiment. The charge on the electron is confirmed by Millikan oil drop experiment. Electron is discovered by what? Whom? J.J. Thomson. Proton identified or observed as H plus by Goldstein, but named by Rutherford. Proton. Neutron discovered by James Chadwick. Nucleus again Rutherford. Okay. X-rays Rontgen. Right. So this is about some concepts from atomic structure. Okay. Thank you, Andy.